start?
Very good. You can start.
Okay.
Can one of the students volunteer to pay attention to time and to document minutes? What's your name? Andre. Andre is the chair.
Okay. Okay, so yesterday, let me summarize briefly some main point. So we saw that if we start with a very simple free conformal field theory and a collection of n complex massless scalar fields, let's say in 3 dimensions. So this I runs from 1 to n, and this phi transforms in the fundamental of some UN global symmetry. And if we look at the UN singlet sector of operators in this theory, then this singlet sector is very simple. There is a scalar operator which I denote as J0, which is just phi square. And then there is a collection of operators with all integer spins, which are exactly conserved operators. So these are bilinears with S derivatives schematically. They are conserved. Okay, so this scalar operator here has dimension 1 in 3 dimensions. In general dimension, it will have dimension d minus 2 if you're in dimension d. These operators have dimension S plus 1, or in general S plus d minus 2. And then we saw that by the usual rules of ADS CFT, this single sector, single trace operators should correspond to single particle states in some ADS theory. And we see that this spectrum is in one-to-one correspondence with the spectrum of the bosonic higher spin theory, Vasiliev theory in ADS4, which has a scalar field I x z with m square equal minus 2 in units of the ADS radius, and the collection of all integer spin gauge fields which are massless. Okay. And we expect that all these fields will interact in some non-trivial way, because from this ADS theory we are supposed to be able to recover the non-trivial correlation functions of these operators. For example, so let me draw a picture which is slightly, I shouldn't go there, that's forbidden. Let me draw a picture which is slightly different from what I was drawing yesterday. So let me denote this plane as the boundary and this as the z direction. Here we have some operators at the boundary, let's say a 3-point function of these operators. We can compute it here by just some simple Feynman diagram, simple free propagator width contraction. But if we want to compute it from ADS, then there will be some non-trivial interaction in the bulk of the fields dual to this object. So this is the bulk of ADS. This is the boundary. And here there is some coupling constant. It's a bit too small. Okay, but the picture is fairly obvious. So is it too small from the back? Anyway, it's just another way of drawing the diagram that I was drawing yesterday, which is the Witten diagram, where we have the operators here and some interaction. And that interaction, if we see how this correlation function scale with n in the dual theory, tells you that the Newton constant in the bulk goes like 1 over n. Okay, just at the end of the lecture, I also said that we could consider a real scalar version of this duality, where we can take just a real scalar fields and consider the ON singlet sector. Then the spectrum of single trace operators contains only even spin currents, and this is in one-to-one correspondence with what is called the minimal higher spin theory in ADS4, which has this which has a scalar field which is the same as there and has all the massless even spin currents. All right. So here, again, I'm writing it in 3 dimensions because that's what I will mostly focus on. But this duality can be phrased in any dimension, and these theories, these higher spin theories, exist in any dimension. We will not write down probably what the general dimension theory looks like. We will write down the 4-dimensional one. But just keep in mind that this theory have a generalization to ADS D+1 for general D. Okay. So any question about this? Yeah, we'll discuss that soon enough. Okay. Before going to the fermions, let me discuss something else interesting. So first, let me say that these dualities between vector models and higher spin theories were first stated in the most precise way by Klebanov and Polyakov. In 2002. So some understanding of the fact that a free field theory should be related to some higher spin theory in ADS was already clear before this work. There was works by Sonborg, Witten, Setskin, and Sandel. But it was Klebanov and Polyakov who first pointed out clearly the special role of vector models in this duality. So as we discussed yesterday, the difference between vector models and general adjoint type models is that the spectrum of single trace operators is very simple, and it's really in one-to-one correspondence with the simplest higher spin theory that you have. Okay? All right. So these dualities are already kind of interesting because if they are correct, they are some example of exact ADS CFT duality, which doesn't involve supersymmetry and doesn't involve string theory, at least not obviously. So from some conceptual standpoint, they are definitely interesting. They may help to understand more precisely how ADS CFT work at some basic level, because we have some very simple duality with very simple spectra, which is much, much simpler than the duality between n equal 4 superior Mills and type 2B string theory, which has a much larger spectrum. But okay, still a duality between free theories, and you may ask whether we can do something more interesting, whether we could discuss some generalization of this, where we have some interacting theory on this side. So this was also one of the main points of the paper by Klebanov and Polyakov, who pointed out that basically in the same framework we can discuss also interacting versions of these vector models. And here I have more space. So instead of now let me stick with real fields for simplicity. Instead of the free ON vector model, we can consider the standard textbook example of interacting version of this model, which is obtained by adding a quartic interaction for the scalar fields. Right? We can add a quartic interaction, right? Now the dimension of this coupling constant, as you can check easily, is 4 minus d, right? In particular, in dimension 3, it has dimension 1. So this deformation of this conformal field theory, of this free conformal field theory, is a relevant deformation, okay, in dimension less than 4. Okay, so in d less than 4, this is a relevant deformation. And as it's well known, this relevant deformation triggers some RG flow from the free theory in the UV to some non-trivial interacting theory in the IR. So there is a flow here UV and here IR. Some RG flow which is triggered by this 5 to the 4th interaction. Here we have the free ON model, and here we have some non-trivial critical ON model, which is some interacting conformal field theory with ON symmetry, which you reach after you do this RG flow. Now, as you probably all know, a standard way to study this flow quantitatively is to use the Epsilon expansion. That's the textbook way, the Wilson-Fisher approach. If you work in D equal 4 minus epsilon, then you can compute the beta function for this coupling constant. Right, and then you see that there is a non-trivial IR fixed point where lambda star is of order epsilon, which solves the beta function equal to 0, and that's this non-trivial conformal field theory, this non-trivial interacting conformal field theory that's here in the IR. So if I work in 4 minus epsilon, that's very close to the free one because the coupling is of order epsilon. So in this framework, this flow is perturbative. But at the end of the day, we are interested in D equal 3, in integer dimension 3, where this is some interacting CFT with ON symmetry. Of course, one could push this epsilon expansion to higher orders, and then there are powerful techniques to resum them and so on and obtain estimates for what dimensions of operators are at this fixed point, for example, in D equal 3. And of course, these ON models are just part of the family of the to which the three-dimensionalizing model belongs that you learned about last week, right? So the three-dimensionalizing model is just the n equal 1 example of this flow, right? Okay. Is this familiar to everyone? Okay, we haven't yet said what this have to do with higher spins, but we will get there soon. So that's one approach, the epsilon expansion. Another approach, I need a big board, so I'll go here. Another approach in which one can study this, these fixed points, which can actually be carried out in any dimension between 2 and 4, and in particular in dimension 3, is to use the Largen expansion. So let me briefly go through this, because if you haven't seen it, this is something which may be useful. So one standard way to treat this quartic interaction in the Largen expansion is to introduce some auxiliary field, right? You probably have, maybe some of you have seen this. So you introduce this field sigma, which is sometimes called Hubbard-Stratonovich field. So you just rewrite that theory by introducing an extra field. You can see that if you integrate out sigma by its equations of motion, you get back the original theory. Now, this action, as written in this form, is more suitable to develop the Largen expansion. And one simple calculation that we can do in the Largen expansion, using this action, is to integrate out now the fields, the scalar fields, because the action is quadratic, and get some effective action for this field sigma. Okay, let me write down here the simple important fact that if you by the equations of motion, this sigma field is related to the phi square field. Okay, that's obvious, it's trivial, but it's important. So now I'm integrating out phi's, and I want to find out what is the two-point function of sigma at the IR fixed point, and that will tell us what happened to this phi square operator in the RG flow. Okay, so now we integrate out phi's. Okay, so if you integrate out phi's, you just get something like this. Right? So integrate out phi's, you get the determinant of the kinetic operator on phi, which is nabla square plus sigma, and then you just exponentiate it. And now you can expand this in powers of sigma. Okay, let me write this as this, where S sigma whereas sigma is the following form. So if you start expanding this determinant in powers of sigma, the linear term is just some tadpole diagram. It's just something like the integral of 1 over p square, and that can be set to 0, for example, in dimensional regularization. So the first term is the quadratic term. So there is, of course, still this s square over 4 lambda there. And then from the term quadratic in sigma, where you expand this determinant, that term can be represented in the following way, which is not difficult to see, and it's left as an exercise. You can write the quadratic term as a double integral okay, where this 0 denotes the expectation value in the free theory. Okay, so if you look at the original action, what happened in the Largen limit when you integrate out phi to leading order is basically that you just you just get sigma sigma and the two-point function of that phi field. But you can see that explicitly by expanding this determinant. So this term is the term which has two propagators, 1 over nabla square sigma, 1 over nabla square sigma, and that's the two-point function. You get one propagator, two propagators. Okay? All right, it's more convenient to write this in momentum space. In momentum space, we get as sigma, now not keeping track of overall constants, which are not very important. Okay, so that's what you get. This term is just this term, okay, and this term is what you get after you do this. You go to momentum space and do this integral in momentum space. Okay, n just comes because you have n in this correlator, right? You have delta ej, delta ji, you get an n. Okay. All right. So this is then there are higher order terms. Here, higher order terms. Okay. But this is enough if we want to know what is the leading two-point function of the sigma field. Okay. So far I'm just massaging this theory and do path integral over phi and get some action for sigma. Now we want to take the IR limit. Okay, so what happens in the IR limit? We want to see what happens at low momenta in this action. Now you see that if we are in d less than 4, then this power is negative, and this term for low momenta is dominant compared to this term. Okay, so in the IR limit, this term that gives a negligible contribution. Okay. All right. That means that in this IR limit of low momenta, we get a very simple kinetic term in momentum space for this sigma, which is just a power of p. And we can invert it to get the 2-point function of sigma. So the 2-point function will just be in momentum space simply the inverse of that kinetic term there. And now you can do a Fourier transform and get the 2-point function of sigma in coordinate space, and that will be some constant, which I didn't keep track of. I just want to know what's the scaling, but you can fix the constant as well. If you do the Fourier transform of this, just do the integral over p with e to the ip dot x, you get this. So we see that in the IR limit, sigma is like a scalar primary operator. With dimension what's the conformal dimension of this operator? 2, right? With dimension 2 plus 1 over n corrections, because this is just a leading calculation, the 2-point function, and we have dropped this higher order terms. Why they are 1 over n? Well, one way to develop the 1 over n expansion is to define the sigma field so that the 2-point function scales like 1. So you could redefine sigma, send sigma over to sigma over square root n. Then you will get a factor of n here if you do that rescaling. And then the leading 2-point function is of order 1, right? Okay, maybe I should... well, in your notes you can write it. I don't want to write the thing again. And then you get powers of n here, right? So after you take this IR limit where you drop this coupling, now you have a new coupling, which is 1 over n, which you can put in by rescaling sigma so that the quadratic term doesn't depend on coupling. So that's the usual way to develop perturbation theory. And then coupling constant goes into the nonlinear terms. Okay, so this calculation that we did just captured the leading order term in the dimension of the sigma. And if you want to get the 1 over n corrections, you have to include corrections to this 2-point function. Okay, there will be interactions in this effective action for sigma, and they will correct this dimension slightly. Okay, so but now let's see what happened. Remember that this sigma field is nothing but phi square operator. But the phi square operator in the UV theory had, at dimension d minus 2, right? And if we are in dimension 3 at dimension 1, okay? And now we see that I was doing this at arbitrary d. So for any d, we start in the UV with this phi square operator having dimension d minus 2. And once we reach the IR, that operator has dimension 2 plus 1 over n correction. Okay? So at large n, we have found this result that here in the UV, so here delta is the dimension of phi I. So in the UV, we start with phi I having dimension d minus 2, right? That's just the bare dimension in the free theory. And once we are down in the IR, that becomes 2 plus 1 over n corrections. Okay, this note that this doesn't depend on the dimension. Okay, so there is always this for any d, this goes from 2d minus 2 to 2 plus 1 over n correction. Okay. You can also see that this is consistent with the epsilon expansion. If you do that, so in the epsilon expansion, everything is more straightforward. You just have the epsilon, usual perturbative epsilon expansion, and here you find, if you try to get the dimension of the phi I operator, you get, I think, 2. Okay, so the epsilon expansion will give you this. Notice that this term is 1 over n at large n. So this agrees with large n, which tells you that result. Okay. Okay, so if you have never seen this, it may be useful to spend some time thinking about it, because I did it maybe quickly. Yes. Okay, thanks. So, yes, but here, so when I do these calculations, I always like to use some regularization scheme in which I don't have to worry about those terms. So, for example, if you use dimensional regularization, it's consistent. If you start with 0 mass, you're not going to generate mass. Okay. If you use some cutoff, then you can put the mass there, and you have to tune it in such a way that the physical mass is 0. But if you use dimensional regularization, if you're interested in the conformal theory, you can start with massless action, and the mass will not be generated. Okay. But of course, physically, yes, you have to tune to the physical mass being 0. But in practice, we can avoid doing that explicitly. Okay. Okay, so this flow actually is just here. There is less stuff to erase here. This example of the Wilson-Fisher fixed points of the ON models is just one special example of a more general story, which is double trace flows. So in general, if we have some CFT and we perturb it by the square of some single trace operator of dimension delta, so O delta is a single trace scalar primary. So that particular case is an example of this, where the CFT here is just a free CFT, and O delta is just this phi I, which is a single trace operator in the language of vector models, and we square it. That's a double trace deformation. So if 2 delta is less than d, then this is a relevant deformation, and that there is a flow. One can show by large n techniques similar to the ones that I did there, that there is a flow from the unperturbed CFT. Let me call this CFT 0. There is a flow from the CFT 0 in the UV to the new CFT, let me call it CFT IR. There is a flow triggered by this, and the general result that you can derive from large n techniques, very similar to what I did here in this specific example, is that the dimension, so the dimension of O delta here in the UV is delta. So this delta just denotes the dimension of this perturbing operator. So this is an operator, of course, which is present in the CFT, and you perturb it by adding the square of it, and delta denotes the dimension in the UV, right? And when you flow down, the dimension of O delta is now d minus delta plus 1 over n corrections. So this can be proved by very similar techniques that I did here, and you can check paper by Gupser and Klebanov, for example, where this is explained in detail. So again, what I just described there is just a special example of this, where the dimension of the perturbing operator is d minus 2, and in the IR I'm getting d minus 2, which is 2 plus 1 over n corrections. Okay? Okay, so this is about CFT. Now, what is the ADS? What is the ADS dual of this deformation? What happens on the ADS side what does it mean adding this deformation and flowing to this new IR fixed point? Well, so this is well understood. So here is some reference, Klebanov, Witten, 99. Well, maybe let me put it, they may have more than one paper in 99. And Witten, are you discussing any of this double trace flows, Joao, in your lecture? Or no? Okay, so let me just explain it briefly. So what happens? So we have in the CFT, so let me recall the basic dictionary. If in the CFT we have an operator of dimension delta, then in ADS we have a scalar field with mass square delta minus d, right? Where this delta is related to how this field scales as you send z to 0, which is the boundary of ADS. Okay, so I'm using Poincare coordinates. This delta is such that as z going to 0, maybe this is small, z to the delta times some function of x plus order of z. Okay, so this delta is related to how this field scales. Okay. Now, when I was discussing the duality between the vector model, the free vector model, and the ADS side, I was just setting delta equal d minus 2, and then check that gives me the right mass. But of course, if you look at this equation, it's quadratic. So if you want to determine what is the delta corresponding to a given mass, there are two solutions, right? So if you just solve that equation for the delta in terms of the mass of the field in the bulk, that's what you get. And typically, in usual examples, it's clear which choice you make. Usually the plus choice is the correct choice because the minus choice will go below unitarity bound in the dual CFT, right? So recall the unitarity bounds. Have you discussed unitarity bounds last week? Yes. So for a scalar operator Well, let me just remind a few of them. Although the one that is relevant right now is just the first one. Okay, so in any CFT, the unitarity bound for a scalar operator is that the dimension has to be greater or equal than d over 2 minus 1, where this is saturated when that operator is a free scalar field, right? Same for fermion here, and where the bound corresponds is saturated for a free fermion, and this is the the unitarity bound for a higher spin operator, which is saturated when the higher spin operator is a conserved current. Right? You can see that this is the dimension, for example, of those bilinear operators in the free scalar theory, which are phi, and that's derivative, right? So it's d minus 2 plus s. Okay, so yeah.
Exclusively 1/2 or
Yeah, I mean 1/2. Maybe. Okay, thank you. Okay, so usually for a generic value of this mass, if you want to describe unitary CFTs, the boundary, the plus choice is the only one that gives you something above this d over 2 minus 1, right? Because typically for generic mass, this will be bigger than 1, okay? But if the mass lies in some special range, so this part of the bound is just the Breiter-Lohner-Friedman bound. It's just so that the square root doesn't give anything imaginary. Okay, so that we always impose if we want some stable theory in ADS. This side is what you have to impose in order to have unitarity, to be above unitarity bound. Okay, so if the mass lies in this range, then both delta plus and minus are above unitarity. And so you can really choose either one of them as your boundary condition for your scalar field. And depending which choice you make, you are describing either side of this RG flow. So you have the same ADS theory in which there is this scalar field with some given mass. If this given mass is between those 2 points, then you have 2 solutions, and the 2 solutions corresponds to these 2 CFTs. Okay. So in the ADS4 higher spin theory, for example, we have seen that we have m square equal minus 2, in units of ADS radius. And you see that this value is indeed in that range. Okay, and then you have 2 choices, so the 2 roots are delta equal to 1 or delta equal to 2. So this corresponds to the, so if you make this choice for your boundary behavior of the scalar field, the dual theory is the free vector model where the phi square operator has dimension 1. If you make this choice, then the dual is this interacting critical theory where the scalar operator has dimension 2, right? So if you make the choice that delta equal to 1, then the dual CFT is the free vector model. If you make the other choice, the dual CFT is the IR fixed point or critical N model. Okay, my notes are disintegrating. Okay, so basically, this was one of the main things pointed out in that Klebanov and Polyakov paper. By adapting something that was well understood for general double trace flows in ADS CFT, by adapting that to this particular case, they pointed out that with the same ADS4 Vasiliev theory, you could describe two dual CFTs, either a free one if you make this choice, or an interacting one, which is this interacting critical M model if you make this other choice. Okay, so but you may ask what happens to the higher spin operators. This is an interacting theory, so we wouldn't expect to have higher spin exactly conserve higher spin operators. Sorry, any questions before? Yeah.
Can we put
You mean along the flow? Yes, you can choose something which is called mixed boundary conditions, in which you have a superposition of both roots. So that's a non-conformal boundary condition for the scalar. It interpolates between the UV boundary condition, the IR boundary condition. Yes, you can do that. Okay, so in this critical CFT, we still have these operators. Schematically. So we still have these operators. They are still primary operators of our CFT, but now they are not exactly conserved anymore. But the way they are not conserved is very special, in the sense that this non-conservation is very small in the large N limit. They are only slightly non-conserved. Okay, so if you look at the equation that the divergence of this operator satisfies in these theories, so this was 0 in the free theory. If you check what it is in this critical fixed point, it's something like this. This is some powers. Let me write it down and explain. So this divergence is non-zero, but it's equal to something which is the product of two single trace operators. So it's a double trace operator. And so here I'm using operators which are normalized so that the 2-point function is 1 at large N. So that's why there is this factor here. So this K just denotes this operator, which here is written schematically. This is a double trace operator. And it's easy to see that if this is the case, if the divergence of the higher spin currents is equal to a double trace operator, it follows that this the conformal dimension of this operator is the one which would be for a conserved current plus 1 over n corrections only, okay, plus some number which depends on S, n plus 1 over n squared, and so on. So there is not a term of order n to the 0. Okay, if this divergence is equal to a double trace operator, then you can show that the anomalous dimension starts at 1 over n. So remember that 1 over n is the coupling constant in the bulk theory. It's like Newton constant. So this, in the dual theory, means that the dual fields are still classically massless, and the anomalous dimensions are generated through loop effects of this type. Where here we have fields running in the loop. Okay. So this is an effect of order 1 over n, because each of these coupling constants here is 1 over root n in this duality, as we discussed. So this explained why at the classical level we still have the same higher spin theory, same Vasiliev theory. We're just changing boundary condition of the scalar field. And this is consistent with what we get here, because the dual fields at the classical level are still massless, and it's only through quantum corrections that we generate a non-zero mass per dump. The way this is possible is that is the fact that in this loop we will have also the scalar field among all other fields. That scalar field has a different propagator, depending whether we choose the first or the second boundary condition. So while this was never checked in detail, it should happen that if you choose this boundary condition, then this effect is 0. But if you choose the other boundary condition, this gives a non-zero shift in the mass, which reproduces this. Okay. So what has been checked is that if you take the difference of the calculations in the two theories, delta equal 1 and delta equal to 2, you do get the right anomalous dimension. But it was not checked that if you just use this, you get 0. Okay, that's assumed. But if that's assumed, then you can see that the difference correctly reproduces the anomalous dimensions. Okay.
Sorry,
yeah.
There
there are no indices. Well, it will take some effort to write down explicitly. It's just so here we have the divergence of the operator of spin s. So this is an object which has spin s minus 1 and has a dimension to leading order s plus d minus 1. So on this side you will have some operator which has the correct quantum number. Okay, so this is just a schematic. S prime will be, so there will be a sum over operators of the same type, where this S prime is not the same as this S, and this J0 is the scalar, in such a way that this thing has the correct quantum numbers. Okay? I'm not writing it down explicitly because it's a little bit, well, it's not that messy, but I don't want to write it down explicitly here. Okay, but it's just schematic. You can see explicitly that this is the structure, and you can actually derive what that operator is if you start from the action of the critical line model written in terms of sigma field. And then you by using equation of motion, you compute what is the divergence of this operator. So you will have the equation of motion for phi will be something like sigma phi I, okay? Let's say with a 1 over root n. In the free theory, that's 0. When that is 0, these operators have 0 divergence. When it's non-zero, you produce something on the right-hand side. Okay, this J0 essentially is this sigma. So if you want to try it, you can just write down the action for the quartic theory in terms of sigma. And that's the simplest way to derive what is this operator here on the right-hand side. Use the fact that the equations of motion become this. Okay. But for our purpose, the explicit form of this operator is not too important. What's really important is just that it's a double trace operator. If this was a single trace operator, if there was some operator that you could write down here, with the correct quantum numbers and there was a single trace, then you would produce a term here of order n to the 0. Okay? So here will become a S. This is absent. If you have theories like n equal 4 superior Mills, what I'm writing here is nothing else but the Caspar anomalous dimension, right? There, the Caspar anomalous dimension starts already at planar limit. Okay? In this case, it doesn't. So this term is not there. In that case, if you look at what is the divergence of higher spin operators, it's equal to some single trace operator of your theory in the n equal 4 case, or in any Yang-Mills type theories. And then you will produce a leading n to the 0 Caspar anomalous dimension. But in these vector models, you don't. That's why at classical level, the dual theory is still some higher spin theory. Masses are only generated through loop effects. Okay? Questions? Yeah. Yeah. No, this is just general, some general CFT with some general deformation. I'm just saying that if that's some operator, some single trace operator, and you deform your original CFT by the square of that, you generate a flow to a new fixed point, and the dimension of the operator in the fixed point is given by this. This is just one specific example of this general story, where O delta is phi I, delta is d minus 2, and so d minus delta is 2. But this is more general. It works in any CFT which has a large n expansion. Then you have this flow. Well, okay. In general, you have to tune the mass term. You have to tune it so that the physical mass is 0 in the IR. As I said before, in practice, most of the time you don't have to do this tuning explicitly if you choose a suitable regularization scheme when you do these calculations of RG flows. Okay. So before there was already a question whether we could do a fermionic version of these dualities, and yes, indeed, you can. So, for example, could consider just a massless Dirac fermion in 3 dimensions, or more precisely a collection of n massless Dirac fermions. Then this theory has a UN symmetry. Again, it makes sense to look at the UN singlet sector. And the UN singlet sector is very similar. There is a scalar operator, which is the operator of psi bar I psi I. This operator now in 3 dimensions, what is the conformal dimension of this operator in this free CFT? Two, right? Because in 3 dimensions the fermion has dimension 1, right? So this has dimension 2. In general dimension, it will have dimension d minus 1, right? Okay. And then there is again a collection of higher spin operators. that you can, you can check that are present in this theory and they are exactly conserved. These operators now have this, they are down indices. These operators now have one less derivative compared to the corresponding scalar story. Okay, so again, the plus dot 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 means terms in which these derivatives are distributed in different ways between this term and this term, such that the full operator is conserved, symmetric, and traceless. Okay, so this is conserved. So what is the dimension of this operator? If it's a conserved current, what should be the dimension in 3 dimensions? Is S plus 1. And of course, so that's the same as in the scalar theory, because in any CFT, if you have a conserved operator of spin S, it must have dimension S plus D minus 2, in 3 dimension S plus 1. And that's why here we have one less derivative, right? Just because the fermions have dimension 1. Okay, so that this is the higher spin operator in this theory. For spin 1, for example, is the usual current psi bar gamma mu psi, which doesn't have a derivative, as opposed to the scalar case, right? Okay, so the spectrum is very similar. And then you can argue in the same way as we did for the scalar theory that this should be dual to some higher spin theory. So that theory should correspond to some ADS higher spin theory with a scalar operator, scalar field. What is the mass? Well, it's the same mass as before, because we already know that delta equal 2 is another root that gives the same mass, right? So it's the same mass. And then there are again the massless fields. So this looks so far the same as what I was writing for the scalar theory, but is it really the same higher spin theory? Well, it cannot be the same higher spin theory. One thing is that the spectrum is not exactly the same, because this operator here is a parity odd operator in 3 dimensions. So this scalar field here is actually a pseudoscalar in ADS4. And moreover, you can see explicitly that correlation functions of operators in this theory, in the CFT, are different from the one in the scalar theory. That means, for example, if you look at the 3-point function of stress tensor in this CFT, again, it will be computed by some Witten diagram, where here we have the graviton. But now this must be equal to TTT in a fermion theory, while before we had that this was supposed to be equal to TTT in a boson theory. And those two structures are different. Right? In a general CFT, as we said last time, you get a linear combination. Now, if you have a dual which exactly corresponds to that, you must just reproduce the fermion structure. And in the scalar case, you must just reproduce the boson structure. So this coupling is different from the higher spin theory that is dual to the scalars. Okay, so we have different cubic coupling from the scalar case. So even though the spectrum look very similar, these two theories are inequivalent. There are two inequivalent higher spin theories in ADS4. And indeed, it was known before this ADS-CFT story was understood. It was known that in Vasiliev construction, there are two inequivalent theories, which were called type A and type B theories. Okay, there's the theory which was called type A. This theory has a scalar, and there's theory which was called type B, which has a pseudoscalar. Okay, this was known before the idea of CFT, that Vassiliev equations have two special type of inequivalent theories that are called type A and type B. So they have almost the same spectrum, apart from this difference, but they have very different interactions. Okay, and we understand this clearly from the point of view of the idea of CFT, because the first variant is dual to a scalar vector model. And the second one to fermion vector model. This was explicitly clarified by Setskin and Sandel and Lee Petko. And this was in the original, the first one was in the original Klebanov-Polyakov paper, but in that paper they didn't discuss the type B theory. In a couple of later papers, people pointed out that there is this type B model, and it has precisely the right structure to be dual to the fermion vector model. Okay. Now, in the same way as in this case, we could describe either the free or critical vector model. Here we also have the two versions, one free and one interacting version. The interacting version is just the so-called critical Gross-Novo model. So the Gross-Novo model is the fermion model with a quartic-fermi interaction. Now, in 3 dimensions, this interaction is irrelevant. So there is, in this case, there isn't a flow from a free UV CFT to an IR interacting CFT. The flow is the other way around. By Largen techniques, you can show in this case that there is a flow from a non-trivial. Here there is a critical fermion in the UV, and in there is a flow to the IR where we have a free fermion. So in this case, the role of UV and IR fixed point is exchanged. But if you treat this theory in the Largen expansion, then things are very analogous to what I did before for the scalar theory. But you have to keep in mind that this is a irrelevant operator now. So what you're supposed to do is actually take the large momentum limit, not the small momentum limit, when you study. So as I did before, you can study this quartic interaction by introducing an auxiliary field, and then that auxiliary field is related to the psi bar psi operator, and you do the same thing, but you have to take a large momentum limit instead of low momentum limit, because this is irrelevant. So in this case, the flow here in the free fermion theory, we have a IR dimension, which is exactly 2, which is the dimension of the psi bar psi operator. And here in the non-trivial UV theory, we have dimension D minus delta IR plus 1 over n corrections, and that's 1 plus 1 over n corrections. Okay? So on the ADS side, again, the story is similar to what I discussed before. You still realize that this pseudoscalar, well, it has the same value of the mass, so we have delta equal 1 or delta equal 2 choice. In this case, the delta equal 2 choice will produce the dual of the free vector model and will give exact higher spin currents. And if you make the other choice, you will have slightly broken higher spin symmetries with the same similar type of non-conservation equation as I wrote for the scalar case. Okay, so let me summarize all this in a table. So we have two models, type A and type V. Those are the higher spin theories. And in each of those models, you have a scalar field with mass square equal -2, and you have a choice of delta equal to 1 or delta equal to 2 scalar boundary conditions. So this is the bulk scalar boundary conditions. So if you make the delta equal 1 choice and have the type A higher spin theory, what's in this box? It's the free UN or ON vector model, where UN or ON will give you either the theory with all spins or the theory with only even spins, right? And delta equal to 2 is the critical ON model or UN. Okay, and in the type B case, the situation is exchanged. I didn't discuss ON in this case, but you, instead of Dirac, you could take Majorana fermions in 3 dimensions, and then you have a theory with ON symmetry, and you then get a spectrum which only has even spins, the same thing as we discussed there. And here you have the critical gross Novo. Okay. So in these two boxes, the higher spin symmetry is slightly broken by 1 over n effects, and that gives non-trivial anomalous dimensions for higher spin currents. And in these two boxes, the higher spin symmetry is exact. Okay. Do I have 1 minute? Okay. So tomorrow we'll see that there is actually a wide generalization of this, which will come out by thinking more carefully about how do we impose the singlet sector restrictions on the CFTs. We'll see that to do that, natural way is to introduce gauge fields, and then instead of these vector models, we will have some gauged vector model coupled with Chern-Simons field, and that will lead to a generalization of these dualities in which we have neither type A or type B, but something in between in the ADS side. Okay? I guess we'll continue tomorrow then. Any question? Yes. So you could combine, you could do something like a type AB model. So you could take a vector model. Let me write it in the free version, right? you could take this simple free vector model, which involves n scalars and n fermions, right? And look at UN singlet sector of this theory. Then there will be, for boson-boson and fermion-fermion, we have the same thing as we had before, right? But in addition, there are half-integer spin operator which are UN invariant. For example, psi bar I, phi I will be dual to some spin 1/2 field in the dual theory. More generally, we can have something like psi bar I derivatives phi I, which will be dual to some half integer, if these are S derivatives, S plus 1/2 higher spin field in the ADS theory. Okay, so that will give you some Vasiliev theory, which involves both bosonic and fermionic higher spin fields. Yeah. Any other question? Yes. Okay. So the critical Gross-Novo model, as the standard epsilon expansion description, is in 2 plus epsilon dimension, because that's marginal there. But there is actually also a description in 4 minus epsilon dimension, which I didn't want to go in in detail because it takes time. We can call it a Gross-Novo Yukawa model, which is an action which involves fermion plus an extra scalar plus Yukawa interaction plus another coupling. You have this model. This model now has two relevant operators in dimension less than 4, which has these 2 operators. So there is in this case there is a flow from a free theory of n fermions plus 1 scalar to an interacting theory in the IR. That interacting theory in the IR can be argued to be the same as the as this UV fixed point that you have here. But in this description is really a more standard flow in which you flow from UV, you have free n size plus 1 scalar, and here you have some in the IR, you have some critical theory, which is equivalent to that theory. Okay, it takes some time to explain why, but one part of the logic is that in this fixed point, we always get a scalar operator which has dimension 1 plus 1 over n corrections, and this can be done in any dimension between 2 and 4 in the large n limit. So this dimension becomes the dimension of a free field if we are in 4 dimension, of a free scalar field. That's why essentially you generate 1 extra free scalar field if you start from being near 4 dimension. But then once you have a free extra scalar field, if you want to do 4 minus epsilon expansion, you have to include all possible terms which are marginal in 4 dimension and relevant below 4. So that's the model you naturally get. And you can make some pretty detailed checks that dimensions of operators at this IR fixed point of this theory are the same as the ones at the UV fixed point of this theory. Okay. Any other question? Okay, so continue tomorrow. Still no higher spins.
You wanted to do more?
Yeah.
What do you do more?
Did this look a lot or? Did I run too fast today? You probably.
I think it's normal.
You probably were working on your stuff.
It always takes time, right?
Oh, yeah.
Can I ask you a question?
Sure.